Greetings, everybody. This video will cover the first set of lecture notes for Chapter 6 in the OpenStax book, Newton's Second Law and Uniform Circular Motion, which I commonly refer to as UCM. And notice we're not going to cover sections 6.4 and 6.6. All right, so, well, when we talk about uniform circular motion, which I'll herefore refer to as UCM, well, the uniform, obviously circular, means it's an object moving in a circle. Uniform means that it's moving in a circle. We'll call the radius of the circle r. But uniform means that it's moving at a constant speed. Its direction is changing because the object's moving in a circle. So at any point along that circular motion, the velocity vector will be tangent to the circle. Here you can see in this sketch of a Ferris wheel, in this case, it's rotating clockwise. And at the bottom, when a rider is at the bottom of the Ferris wheel, notice the velocity vector is always tangent to the circle. So notice the velocity vector is in the negative x when a rider is at the bottom. The velocity vector is in the positive x when the rider's at the top. So the direction is changing, but the magnitude, the speed doesn't change. Well, remember, if the direction and or the speed of an object changes, it is accelerating. So anything undergoing UCM is accelerating. Now again, the circle that the object is moving in could be in the horizontal or vertical plane. For example, here's a Ferris wheel. Clearly, the riders are moving in a vertical circle. Now here's what's commonly referred to as a spherical pendulum. It's a mass, typically a spherical mass at the end of a string, and it's being swung such that the ball is moving in a circle in the horizontal plane. So it's moving in a horizontal circle. Okay. Well, for an object to undergo UCM, there has to be a force or forces. In other words, there has to be one or more force that keeps the object moving in the circular path. Let me just zoom in a little bit. There we go. Now notice here, it looks like it's some type of a hockey puck at the end of a string or whatnot. But notice, and in this case, notice in both cases, see the gray shaded arrow here? That's simply telling you that when you're facing the page, the object is moving in a circle, it's moving clockwise. Likewise here. That shaded arrow means that the Ferris wheel is rotating clockwise. Here it doesn't really matter, it's in the horizontal circle. But there must be one or more forces that keep the object moving in a circular path. Well, we refer to those forces in general as the radial forces, hence here the F with the subscript R. Sometimes radial and centripetal mean the same thing. So if I go back and forth between radial or centripetal, don't let that confuse you. Words. Now, the sum of the radial forces indicated by FR, the subscript R meaning radial, well, they're always going to notice, no matter what, the net radial force, no matter where the object is on the circle, the net radial force must be directed towards the center. Now we call the acceleration, I call it, as again, remember, any object undergoing UCM is accelerating. Well, typically we call this acceleration the centripetal acceleration, A with a subscript C. Now, centripetal I prefer to radial because centripetal comes from the Latin for center seeking, i.e. towards the center. And the net radial acceleration or centripetal acceleration is no matter where the object is on the circle, it's always directed towards the center. So the purple vector representing AC towards the center, the blue vector representing the net radial force towards the center. Now remember, the direction of the velocity is changing, but its magnitude remains the same. So if v is 30 meters per second, it's 30 meters per second no matter where the object is as it's undergoing UCM. Well, the magnitude of AC, the magnitude of the centripetal acceleration, AC is equal to v squared over r, where r is the radius of the circular motion and v is the magnitude of the velocity. It's the speed in meters per second. So AC is v squared over r. Now again, we're going to do a lot of examples where we have something moving in a circle. We want to draw all the forces acting on it. Again, no matter if it's a UCM problem, inclined plane, Newton's second law for connected masses, doesn't matter. You have to draw all the forces acting on the object. If you can't draw them, how can you get their components? And you need their components because you have to apply Newton's second law in the x direction and the y direction. And we'll find out also in what's called the radial direction. Well, the radial direction for UCM, the positive radial direction is defined as any force that's moving that's directed towards the center of the circle. By definition, in terms of the radial direction, that's positive. You don't want to think of positive x and negative x, positive y, negative y. If something's moving in a circle, if a force is directed towards the center, it's positive. And obviously, if the negative radial direction is away from the center, any force directed away from the center is positive. Well, let's look at the example of the conical. I said spherical. It's the same thing, but the spherical pendulum or conical pendulum. It's simply a mass hanging at the end of a string. Somehow the string is being swung such that the mass at the end of it is moving in a horizontal circle. Remember, at a constant speed. Okay, well, so for the conical or spherical pendulum, the only two forces acting on the object are its weight, mg, in the negative y direction, and again, mass connected to a string, there's a tension force. See the tension force T, and remember it's directed away from the object but along the string. And because the speed is constant, the radius of this horizontal circle will never change, and the angle will never change because the speed is constant. So that guarantees you that theta and r will not change. And obviously L, the length of the string, that will not change. All right, let's analyze the conical pendulum. Again, here it is redrawn right here. And again, spherical, conical pendulum mean the same thing. It's just the path of the ball at the end of the string. It's moving in a horizontal circle. So this is like you're looking straight ahead. It's an edge-on view of this horizontal circle. Well, again, the only two forces acting on the ball are mg and t. L is simply the length of the string. That's the length from where the string is attached to the support to where it's attached to the ball. Well, notice the tension force, and again, angle, theta is the angle that the string makes with respect to the vertical. Again, for UCM, theta, no matter where the ball is on this horizontal circle, UCM means that angle theta will not change. L does not change, obviously R does not change. Well, the tension force has two components. The horizontal component of the tension force is T sine theta, because remember, see, there's theta. The horizontal component of the tension force is opposite, so it's T sine theta. The adjacent, or the vertical component of the tension is adjacent, so it's T cosine theta. Well, notice, remember here, this object is moving in a horizontal circle. It's undergoing UCM. Well, notice T sine theta is directed towards the center of the circle. In terms of the radial direction, T sine theta is positive, because no matter where the ball is on this horizontal circle, T sine theta will always be directed towards the center. But right now, here the ball is on the right here on the upper, the leftmost part. When it's over here, T sine theta will be directed, again, it's always directed towards the center. Now, remember, the ball is moving in a horizontal circle, so it is not accelerating in the y direction. So clearly, T cosine theta must equal mg because the ball is not moving. It's not accelerating in the y direction. So again, in terms of the radial direction, T sine theta is positive. Doesn't matter where the object is as it's moving in this horizontal circle. T sine theta is always directed towards the center. So now let's look at the Ferris wheel. Let's look at the force it's acting on, and we'll treat the chair and the person riding in it as just one object. No, scratch. Forget that was nonsense. No, afraid I said that. Let's just look at the Ferris wheel example, and we're going to look at all the forces acting on the rider when they're at the bottom, and 2 when they're at the top. So let's look at, forget what I said about treating the chair and the rider as one object. No, we're just looking at the forces acting on the person sitting in the Ferris wheel chair. Okay, let's look at that. Well, here, let's look at the person first when again, here, the Ferris wheel is rotating, in this case, clockwise. And let's look at first the forces acting on the rider when they're at the bottom of the Ferris wheel. Well, remember, there's mg, the weight of the rider. That's always in the negative y direction. Now, Fn bottom, that's the normal force of the chair pushing on the rider. And BOT means that's the normal force when the rider is at the bottom. But remember, person in contact with the surface, i.e. they're sitting in this chair, the force of the chair acting on the rider, clearly that green vector representing Fn bottom, clearly it's perpendicular to the surface of the chair where the person's sitting. So in terms of the radial direction, Fn bottom is positive because it's directed towards the center of the circle. Mg is negative because it's directed away from the center. So here, Newton's second law for UCM, and what it does is it states that the sum of all the radial forces equals the mass times the centripetal acceleration. And remember, centripetal radial mean the same thing. So the sum of the radial forces equals m times AC. Well, what is AC? V squared over r. So the sum of the radial or centripetal forces equals mv squared over r. Well, remember, with FC, FC and FR mean the same thing. So don't let that throw you. Centripetal, radial, in terms of physics, they mean exactly the same thing. So let's apply this to the bottom of the Ferris wheel. Well, Fn bottom is positive because it's directed towards the center. Mg is negative because it's directed away from the center. So Newton's second law for UCM yields Fn bottom minus mg equals mac. Well, what is AC? AC is v squared over r. In this case, we're calling the radius of the Ferris wheel motion. It's large r. Doesn't matter. So that's mv squared over r. Right here. Sum of the forces in the centripetal. The sum of the centripetal forces equals mv squared over r. Remember, again, can't stress this enough. Radial, centripetal, same thing. But away from the center is negative, towards the center is positive. Now let's look at the person when they're at the top. Well, mg never changes. When the person does that, there's their weight, mg, again pointing always in the negative y direction. Now notice when they're at the top, Fn, that's the normal force of the chair pushing on the rider. So Fn top is indicated by this green vector here. Notice that green vector is clearly perpendicular to the surface of the chair where the person is sitting. Well, again, Newton's second law for UCM, right here. The sum of the radial forces must equal mv squared over r. Remember, radial forces towards the center is positive. Remember, I'm looking at the top now. So mg is towards the center, it's positive. Fn top is directed away from the center, it's negative. So that's Newton's second law for UCM. And that sum always equals m times v squared over r, where m is simply the mass of the rider. R is the radius of that UCM. In this case, we're using a large R, doesn't matter. And V is the speed of the Ferris wheel. So notice Newton's second law for UCM. It has a different form depending upon whether the rider is at the bottom or at the top. Remember, we have to think now radial direction. Anything towards the center is positive. That's why when we're at the bottom, normal force bottom, that's positive, minus mg equals m v squared over r. Then when you're at the top, mg minus fn top equals mv squared over r. Remember, so you can't necessarily, you want to think outside the box a little bit. You know, why does Newton's second law for UCM, why is it this equation when the rider's at the top, and why is it this equation when the rider's at the bottom? That's what you want to understand that. That's what you want to come away with after viewing this video. We're up to 16. Let me save this video and get it posted.